Now we come to part 2 of the videos, which we are going to go into in-depth into industrial hygienes. And in this part 2, we are going to talk about anticipations and identifications and also the industrial hygiene evaluations. First part of this second videos will talks about the data useful for health identifications, and also I'm going to introduce to you what is safety data sheets, how do we interpret this data sheet, and also how do we gather information and use that as part of our evaluation process. And the second part of this videos, we are going to talk about the evaluations in terms of calculations. How do we calculate the threshold limit values for 8 hours and for all the operators? And for these videos, we also have a part 3 videos, which we are going to talk more about the control systems. How do we prevent it? What are the PPE to be used and the lab inspections and audit? One of the major responsibilities of the industrial hygienist is to identify and solve potential health problems within the plants. Chemical process technology, however, is so complex that this task requires the concerted efforts of industrial hygienists, process designers, operators, laboratory personnel, and management. The industrial hygienists help the effectiveness of the overall programs by working with these people. For this reason, industrial hygiene must be part of the education process for chemists, for engineers, and the managers. Many hazardous chemicals are handled safely on a daily basis within chemical plants. To achieve this operating success, all potential hazards must be identified and must be controlled. When the toxic or flammable chemicals are handled, the potential hazardous conditions may be numerous. In the large plants, there may be thousands. In order to be safe under these conditions, it requires discipline, skill, concern, and attention to detail. The identification step requires a thorough study of the chemical processes, operating conditions, and operating procedures. The sorts of information including process plant description, the operating instructions, safety reviews, equipment vendors description, information from the chemical suppliers, and also information from operating personnel. The quality of this identification step is often a function of the number of resources used and the quality of the questions asked. The different resources may have different operating and technical emphasis unique to piece of equipment or specific chemicals. This identification step it is often necessary to correlate and integrate the available information to identify new potential problems resulting from combined efforts of multiple exposure. During the identification steps, the potential hazards and methods of contact are identified and recorded. As shown in these slides in the table 3.7, the potential hazards are numerous, especially because the listed hazards can also act in combination. This list of potential hazards together with the required data for hazards identifications is commonly used during the identification steps of industrial hygiene process, as can be shown in this table here, the data useful for health identification. One of the most important references used during an industrial hygiene study involved toxic chemicals is the material safety data sheet. We used to call it MSDS, but the new one currently that is being standardized is called SDS, the safety data sheet. So the SDS lists all the physical properties of a substance that may require to determine the potential hazards of the substance. So there are a total of 16 sections in the SDS. And all these SDS are available from the chemical manufacturers themselves or you can get it from a commercial source or a private library developed by the chemical plant. So we are going to go into details of each sections in the SDS. Sections 1 talk about the identifications, like the basic informations of the products, including the manufacturer's or the distributor's name, their address, their phone number, etc. Sections 2 talks about the hazards identifications regarding the chemicals and also the required labels elements. And sections 3 go into details about the compositions and informations on the ingredients. Sections 4 is a specific sections talk about the first aid measures. What is required if, let's say, someone's get exposures to these chemicals and the symptoms, be it immediate or delay of an exposure. Sections 5 is specifically used for firefighting measures, the techniques and equipment recommended for extinguishing a fire involving this particular chemical during combustion. Section 6 talks about the accidental release measures, so the step to take in the event of a spill or release involving the chemicals. This includes the emergency procedures, the PPE that is required, and the proper methods of containment and cleanup. Section 7 talks about the handling and the storage of this particular chemical. Section 8 is what we often use, talks about all the exposure limit. So if you want to do any calculations to estimate what is the threshold limits, refer to Sections 8. Sections 9 give us the ideas of the physicals and chemical properties of the chemicals. Sections 10 talk about the stability and the reactivities of this hazardous chemical. Sections 11 give us the information on toxicology, so the route of exposures, be it inhalation, ingestions, or absorptions, and the symptoms, and also the acute and chronic effects. Section 12 of the SDS sessions gave us the ecology information, so how does the chemical affect the environment and the durations of the effect. Section 13 is specifically talk about how do we dispose these chemicals, talk about the safe handling of waste and method of disposal, and including the disposal of any contaminated packaging. Sections 14 is about the transportation's information, talk about packing, marking, labeling required for hazardous chemical shipment. Section 15 are all the regulatory informations that applies to this particular chemical, and Section 16 is other information. The evaluation phase determines the extent and the degree of employee exposure to toxicants and physical hazards in the workplace environment. During the evaluation phase, the various types of existing control measures and their effectiveness are also studied. So during the evaluation study, the likelihood of a large or small leaks must be considered. For example, a sudden exposure to high concentrations through large leaks may lead to immediate acute effects such as unconsciousness, burning eye, or fit of coughing. There is rarely lasting damage to individuals if they are removed promptly from the contaminated area. So in that case, ready access to a clean environment is very important. In order to establish the effectiveness of the existing control, samples are taken to calculate or determine the worker exposures to conditions that may be harmful. If problems are evident, control must be implemented immediately. Temporary controls such as personal protective equipment, or what we call PPE, can be used. Long-term and permanent controls are subsequently developed. After the exposure data are obtained, it is necessary to compare to the actual exposure level to the acceptable occupational health standards, such as TLVs, PELs, or IDLH concentrations. These standards, together with the actual concentrations, are used to identify the potential hazards requiring better or more control measures. A quick recap of what we have talked about last week on the threshold limits value, TLV values. Remember we mentioned that there are three types of TLV. One is TWA, which is the values that is safe for the workers to expose up to 8 hours a day and 40 hours a week. And the second levels of exposures limit is what we call the STEL's limit. That is a short-term exposure limits, which remember we have the 15 minutes exposure and the 1 hour gap and another 15 minutes exposures, and maximums they can only expose up to 60 minutes a day within this exposure limit. And there's the third level, which is what we call the ceiling values, where if the concentrations exceeded this, no workers are allowed to be in the workplace until we bring down the level. A direct method for determining workers' exposure is by continuously monitoring the air concentrations of the toxicants online in the work environment. So the continuous concentration data can be calculated by using this formula shown in this page. And the integral is always divided by 8 hours, independent on the length of time actually work in the shift. So for example, if a worker is exposed for 12 hours to a concentration of a chemical equals to the TWA, then the TWA has been exceeded because the computational is being normalized to 8 hours. Continuous monitoring is not the usual situations because most facilities do not have the necessary equipment available. So for that case, for the intermittent samples to be obtained, representing workers' exposures at fixed point in times, if we assume that the concentrations is fixed over periods of time, the TWA concentrations can be calculated using this formula's equations 3.2 as shown in the slides. All the monitoring system has a drawbacks because first, the workers move in and out of the exposed workplace. Second, the concentrations of toxicants may vary at different locations in the work area. So it is important for us to know where is the placement and the selections of placements of this monitoring equipment and the interpretations of data. If more than one chemical is present in the workplace, one procedure is to assume that the effects of the toxicants are additive, unless other information to the contrary is available. So the combined exposures from multiple toxicants with different TWAs is calculated from this equations 3.3 as shown here. So if the sum in this 3.3 is more than 1, then the conclusion is that the operators or the workers are overexposed. If the summations of concentrations of the toxicants in the mixture exceeded this amount, then the workers are also overexposed. So for mixtures of toxicants with different effects, such as an acid vapor mixed with a lead fumes, the TLV cannot be assumed to be additive. So now we have an example here, example 3.2. Air contains of 5 ppm of diethylamine, which have a TWA of 5 ppm, 20 ppm of cyclohexanol with a TWA of 50 ppm, and 10 ppm of propylene oxides with a TWA of 2 ppm. What is the mixture TWA and has this level been exceeded? So there are two methods to do this. Let's look at method one by one. So since they are asking about the mixture TWA, so TLV, TWA mixture. We can use these formulas of total CI over total CI of TWAI. In this case, we have 5 plus 20, so this is 5 here, 20, and we have 10 here. So 5 plus 20 plus 10 ppm over 5/5 ppm plus 20/50 ppm plus 10/2 ppm. So this will give us 5.5 ppm. So in this case, the TWA mixture is 5.5 ppm. So has this level been exceeded? So we have to calculate the total concentration. So we have 5 ppm plus 20 plus 10, total of 35 ppm. And this level is definitely way larger than the TWA mixture. Therefore, in this case, this is exceeded. Okay, this is method 1. So there is also another method to calculate this by using the equations 3.3. 3.3 says that as long as this total summations of CI over TLV, TWAI is less than 1.0, then it is not exceeded. So let's calculate total summations of CI over TWAI. So we have 5 ppm over 5 plus 20 over 50 plus a 10 over 2. So the total here is 6.4. And again, this is way larger than 1.0. So again, this value shows that this level is exceeded. So this is another example. To calculate the 8 hours TWA worker exposure if the worker is exposed to taurine vapor as follows. So it's given the durations of exposures and the measured concentrations at different time interval. So in this case, we will be using the TWA data, that is summations of CI TI over 8 hours. So in this case, we will have concentrations of 110 that exposed for 2 hours plus 330 exposed for another 2 hours plus a 90 that exposed for 4 hours over a duration of 8 hours. Total here, if you calculate, it will give us 155 ppm as an average value, TWA value. So let's go to appendix AG-1. You will find that taurine has a TWA value of 20 ppm. So in that case, this value is way larger than 20 ppm. So again, in this, it means that this is exceeding. In other words, PPE, or we as an engineer, we need to take actions to reduce the concentrations of the said exposure. Industrial hygiene studies include any contaminants that may cause health injury, such as dust or even sound. Toxicology theories teach that dust particles that present in the greatest hazards to the lung are normally in the respiratory particle size range of 0.2 to 0.5 micrometer. Particles larger than 0.5 micrometers are usually unable to penetrate the lungs, whereas those smaller than 0.2 settle out too slowly and are mostly exhaled with the air. Noise problems are also common in the chemical plants. These type of problems are also evaluated by industrial hygienists. If a noise problem is suspected, industrial hygienists should immediately take the appropriate noise measurements and develop recommendations. Thus, calculations are performed in a manner identical to that used for volatile vapors. Instead of using ppm as the concentration unit, we can use either milligram per meter cube or millions of particles per cubic foot in this case. So example 3.5 shows us two different types of dust, and for us to calculate the TLV level of this dust A and B. So for us to calculate TLV, we use back the same formulas where total of concentrations over total of concentrations divided by TLVI over here. So in this case, we have 70%, 0.7 plus 0.3 over 0.7 divided by 20 plus 0.3 divided by 2.7. And in this case, we have the data of 6.8 since it's talk about this MPPCF unit. So there you go. So the TLV mixture for this mixture of particles dust A and B is 6.8 millions of particles per cubic foot. An absolute sound scale in dBA for absolute decibel is defined by establishing an intensity references. For convenience, the hearing threshold is set at 0 dBA. So table 3.7 shows us the dBA levels for a variety of common activities. And the permissible noise exposure level for a single source are provided in this table shown in this slide. So that's the sound level on dBA and the maximum exposures at this level. Example 3.6 here is for us to calculate the decibels noise level, the mixture of noise level. So to determine whether the following noise level is permissible with no additional control measure. So it's given that the noise level at 85, the durations of 3.6 hours, and the maximum allowed limit is given. So for us to calculate, again, we use back the same formula. Total would be concentrations over TLV, TWAI. In this case, we will have 3.6 as the duration over 16 plus 3.0 over 4 plus 0.5 over 0.5. And if we calculate this whole thing out, give us 1.97, which we can see that this level is more than 1.0. In this case, since it's more than 1.0, the employee in this environment are immediately required to wear a ears protections. On a longer term basis, noise reduction control method should be developed for the specific piece of equipment with excessive noise level. The best procedures to determine the exposures to toxic vapor is to measure the vapor concentrations directly. For design purpose, estimates of vapor concentrations are frequently required in enclosed spaces or above open container or where the fuels are filled and the area of spills. So you can see from this figures 3.9 here, it shows us the enclosed volume, and the enclosure is ventilated by a constant volume airflow. So the volatile vapors are evolved within the enclosure, an estimate of the concentrations of the volatile in the air is required. So the formulations is given as per equation 3.9 here. C is the concentrations of volatile in the enclosure. V is the volume of enclosure. QV is the ventilation rate, where K is the non-ideal mixing factors, where QM is the evolution rates of volatile materials, and M is the molecular weights of volatile species. This equation 3.9 is used to determine the average concentrations in ppm of any volatile species in an enclosure given a source term Qm and the ventilation rate of Qv. So therefore it can apply to the following types of exposures, be it a worker standing near a pool of volatile liquid, or a worker stand near an opening of a storage tank, and also a worker standing near a pool of open container of volatile liquid. And with these assumptions included, the calculated concentration is an average concentration in the enclosure. The localized conditions could result in a significant higher concentrations. So for example, workers who stand directly above an open container might be exposed to a higher concentrations compared to a worker standing far from that container. And also another assumptions made is that the steady state condition is assumed. And also the non-ideal mixing factors varies between 0.1 to 0.5 for most practical situations. And the perfect mixing conditions is K is 1. The next example shows you the calculations to calculate an open taurine containers with functions of time, and to estimate the concentrations of taurine vapors in the enclosures, and compare your answers with the TRV for taurines of 50 ppm. So you can take a look how the solutions is done. That I'm not going to go through step by step here. It's very straightforward. For vessels being filled with liquids, the volatile emissions are generated from two sources, which are shown as this following. First, the evaporations of the liquids, and also the displacements of the vapor in the vapor space by liquid filling in the vessel.